Today we're going to talk about how we compare models in statistics. We're going to talk about it in the general terms of model testing frameworks. So when we have data, that's telling us what happened in the real world, but it doesn't tell us how it happened or why it did. Data are a pattern that we can observe. A data set is a pattern that we have observed, but the process that created that pattern, the system in which that pattern appears, is not something that we see directly in the data. It's something that we have to infer from the data. And the things that we use to do those inferences are models. Each model represents an alternative explanation of what's going on in the real world, what system or process produced the pattern that we see. And so in order to test those models to see which one is the most reasonable explanation for the data that we have to compare them to each other. And there are many possible ways that we could do this comparison, but the one that is we're going to focus on in this course is testing those models by taking the model and seeing how well it fits. So if the blue peg is the data, then the circular model on the left is not a good fit for the data, but the square one on the right is a good fit. So we would say that since that one is a better fit, we say it's a better candidate for explaining the real-world process that led to the data that we collected in the form of a blue peg. So that's a nice visual metaphor, but it turns out that there are actually lots and lots and lots of different ways we can quantify the best fit. And of course we want to quantify things because this is statistics and we work with numbers. So the quantification that we are going to talk about next, and it's a pretty useful one, is the likelihood ratio. So we've talked about likelihoods already a couple times in this class. We talked about how if you have a model with a variety of different parameters, you can often compute the maximum likelihood estimate, the parameter for which the model has the highest likelihood given the data. So, for example, here we have a series of models where the probability of heads runs from 0 to 1, and we have the likelihoods of those models given the data set that there have been 2 heads and 3 tails. And so you can see that here around 0.3 is where it reaches its height because 2 out of 5, it's at 0.4, excuse me. Here around 0.4 is where it reaches its maximum because 2 out of 5 is 0.4. You can also see that there are a lot of other possible things that have very similar likelihoods. Now, if we had 100 times as much data, we have 200 heads and 300 tails. So our maximum likelihood estimate, again, is 0.4. But here, we can see that the range of values that are similar is much narrower than when there's a small amount of data. And to quantify that, we can take this maximum and divide it by the value at each of these other places, and that will give us a likelihood ratio. How much better is the best estimate than some of these other ones? So we'll see in the next slide. Here it is. So here down here at 1, that is where the maximum likelihood occurs. And then as this number gets bigger, that means that the maximum likelihood estimate, so if we go up here, this is 2, so that means here, the maximum likelihood estimate is roughly twice the likelihood that, like, say, 0.68 does, or 0.2 over here, when n is 5. But that double likelihood is closer. It's maybe like 0.45 and 0.35 here when you have a, well, it's probably like 0.42. But anyway, there's narrow range where the likelihood is twice as good, or 10 times as good. So this likelihood ratio lets us compare how good the fit is. And notice that both, before, I'm going to go back a slide, these likelihoods by themselves were affected by the peak here, the location of the peak, was affected by the sample size. The likelihood ratio is 1 for both of these. So we're sort of partially accounted for different sample sizes here by looking at these ratios within the model, given that set of data. So likelihood ratio is a way of saying, look, our data are, this model here is twice as good as that model in the red case, and it's twice as good as that model in the blue case. So you can choose what threshold of likelihood ratio you want to use, and 2 or 3 is often used in stats, and say, okay, well, my model is twice as good as theirs, or this parameter is twice as good as that one, so we would say, with 5 coin flips or 500 coin flips, we're not totally sure that probability is 0.4, but if you're 0.5, you say, well, it's within this region of like 0.2 to 0.6, and if you have 500, you could say, well, it's between this region of 0.35 and 0.42 or something like that. So it gives you an area where you can say, I'm pretty happy about my estimate. So that is how you use likelihood ratios. And once you have those likelihood ratios, then as long as you're within the same model family, as long as you're saying, all right, it's a Bernoulli process, so I only have one parameter I'm trying to estimate, what's the best parameter, then that likelihood ratio is good. It also can be very useful when you are working with something that's not like a simple Bernoulli or normal distribution process, where it's a complicated model and you don't know for sure what the actual maximum likelihood estimate is. You can use likelihood ratios to get close to that with some numerical tool where you approximate, you estimate the parameters, compute a likelihood, then maybe tweak the parameters, compute a new likelihood, and keep doing that until the likelihood doesn't get much better. The likelihood ratio doesn't improve much, and then you'd be good. However, when you have different numbers of parameters, if you're comparing like a normal distribution model when there are 2 parameters to a chi-square distribution model, there's only 1 parameter, you can't really use likelihood ratios because the models have different parameters, and so you're kind of comparing different objects, and it's like an apples and oranges thing. So in that case, you can't use likelihood ratios, and I will talk next about the kinds of things you can use